Flow meters respond to the bulk flow rate, even in multi-phase flow. A turbine or spinner rotates as a function of the rate at which fluids flow past it. If the spinner response in a static fluid is plotted in revolutions per second for several logging speeds, both up and down, the relationship is linear. The lines do not, however, go through the origin. The cause of this shift is the viscosity of the fluid. Greater viscosity tends to cause a greater shift. When the spinner encounters an upflow, as would be expected in a producing well, the effect is to shift the response curve of the tool to the left by an amount equal to the upflow velocity.
The flow velocities measured are those seen by the spinner turbine blades. If the spinner is centralized, and it should be for best results, it has sampled the flow from the center of the well bore, but too high, which is not representative. As a result, a flow profile correction factor must be used, typically 0.83.
To compute the bulk flow rate in barrels per day or cubic meters per day, one must multiply by the proper conversion factor and wellbore ID squared. The cumulative bulk flow for different entry points is determined by difference. For multi-phase flow, once the bulk flow rate and holdup of the phases are measured, the slippage velocity of the light phase through the heavy phase must be determined. The relationship for slippage velocity is a function of holdup and fluid density difference. For example, for an oil density of 0.7 grams per cubic centimeter, a water density of 1.0 grams per cc, and a water holdup of 0.70, the slippage velocity of the oil with respect to the water is about 19 feet per minute, 5.8 meters per minute. When dealing with a gas-liquid system, a slippage velocity of 60 feet per minute, 18.3 meters per minute, can be assumed.